In this lesson, we dive into something called implicit differentiation. Now, this process of differentiating is going to be so important and is going to allow us to find the derivative of a lot of functions, and a lot of important functions. So this is implicit differentiation. Now, if you look back over our previous lessons and previous examples, if you look through your notes, you'll find that most of the functions we've been dealing with so far, most of the ones that we've been looking at, have been described by an equation of the form y equal to f of x. That is, that y is explicitly defined in terms of the variable x. Y is explicitly defined in the variable x, but what happens when we have y, an equation that wherein y is implicitly defined? Something like this: x cubed plus y cubed minus 9xy is equal to 0. Here, there's an implicit relationship between x and y. The same is the case here. Y squared minus x is equal to 0, or x squared plus y squared minus 25 is equal to 0. These equations are just a few examples that define an implicit relationship between x and y, meaning that the value of x determines one or more values of y. So that is to say, if you solve for y, you're going to get one or more values for y. Also, sometimes it's really, really, really difficult, sometimes impossible to solve one of these equations or equations like these for y. So implicit differentiation is going to allow us to differentiate equations like these, and we won't even have to solve for y, which is really, really great. Now, when we get into, or right before we get into our first example of looking at what implicit differentiation looks like, it's very important that you and I know that we are going to assume that the equation we're looking at determines y implicitly as a differentiable function of x. So y, please consider y to be a function of x. Y is a function of x, so that dy dx exists. All right, so just remember that y is a function of x. All right, so let's look at our first example. All right, so look at this. Find dy dx, that is the derivative of y with respect to x, if y squared is equal to x. First of all, I would love for us to consider graphically what the equation, or excuse me, what the graph of this equation looks like. Because y is being squared, we know it's a parabola opening sideways. And we know that it will be opening to the right and its vertex will be at the origin. Now, in order to find dy dx, what we want to do is we want to solve for y. But notice what's interesting here is when we solve for y, we get two different differentiable functions of x. In other words, when we solve for y, you would take the square root of both sides and you would get y is either equal to positive x or y is equal to the opposite of the square root of x, right? Y is equal to the positive square root of x is what I should have said, or y is equal to the negative square root of x. And just to differentiate one equation from the other, I'm going to use subscripts. So I'm going to call this y sub 1, and then I'll call this y sub 2. Now, notice we have two different differentiable functions here, and so we know how to find or how to calculate the derivative of each of these, right? And so, we would do dy sub 1 dx is equal to 1 over 2 root x, right? That's the derivative of this first equation, right? And then the derivative, and I hope you feel comfortable with finding the derivative of the square root of x. You can use the power rule to do that. Also, for this one, it would be a different derivative, right? So dy sub 2 dx would be equal to negative 1 over 2 root x. So notice that we have two different derivatives, right? So this one here, notice that this is for the positive square root of x. So this derivative here, it must be clear to us what this derivative is giving. This derivative here is giving the slope of any line that's tangent to the upper half of this curve, because this represents the positive square root, so it's this upper half. This derivative here is giving us the slope of any line tangent to the lower half of the curve. So here's the graphical representation of what we've done so far. We have two different derivatives, okay? This first derivative, again, is giving us the slope of any line tangent to the upper half of our curve. The second derivative is giving us the slope of any line tangent to the lower half of our curve. Now, what we want to achieve with implicit differentiation is the following. We would like to have one single derivative for the slope of the line tangent to any point along the curve. We don't want to have two different derivatives. We want one single derivative. In addition, we would like to find the derivative without having to solve for y first. You know, for this equation, solving for y was really not that big a deal, right? Taking the square root of both sides. But you're going to see, hopefully, in the future examples that solving for y is not convenient. Solving for y is downright difficult. So you and I would like to find one single derivative for the slope of any line tangent any tangent line to any point along the curve. And we would like to do that, find that derivative without solving for y. So let's see if you and I can do that right now. So suppose we knew only the following. Suppose we didn't know what these derivatives were, okay? And suppose we knew only that this equation right here, y squared is equal to x. Suppose we only knew that this equation defined y as one or more differentiable functions of x, okay? But we didn't know what these two derivatives were. Okay, we didn't know what these two functions here were. Can we still find these derivatives? So consider the following. This is the equation they gave us to start with. Let us differentiate both sides of the equation with respect to x. Now be careful, when we differentiate both sides, remember that we are treating y as a function of x. All right, so let me move this up just a little bit here if I can. Yeah, all right, cool. So let's differentiate both sides. So it'll look like this. When I do the derivative of this left-hand side, I must find the derivative of the right-hand side. All right, very good. Now, this is going to be the chain rule, because remember, y is treated as a function of x. So it'll be the power rule and the chain rule. So the power 2 comes down, and now y is being raised to the power of 2, that power, minus 1, which is 1, times the derivative of y with respect to x. Remember, y is a function of x. So the derivative of y with respect to x is basically dy dx. And the the right-hand side is 1. The derivative of x is 1. The idea here is now to to isolate dy dx. Solve for dy dx. That's what we want anyway, right? We want to find the derivative of this function. So solve or isolate dy dx, which means divide both sides by 2y. So then what we get is dy dx, the derivative of y with respect to x, is 1 over 2 times y. Now this is awesome because now we only have one derivative, right? This one derivative can be used to find the slope of the line tangent to any point along our curve. Whereas before we had two different derivatives and we had to solve for we had to solve for y. We found this one derivative and we never had to solve for y in the beginning. All right, check this out. Find the slope of the circle x squared plus y squared equal to 25 at the point 3, negative 4. Now, x squared plus y squared equal to 25. This equation defines a circle whose center is the origin and whose radius is 5. Now, the circle is not the graph of a single function of x. Actually, it's the combined graphs of two differentiable functions, right? So this is a perfect equation for us to use implicit differentiation. All right, so this is the graphical representation of what we are doing. We are finding the slope of the line tangent to this circle at the point 3, negative 4. Now, if we try to solve for y first, now before I use implicit differentiation, allow me to solve for y first. Now, this is not implicit differentiation, but what I want to do is I just want to contrast solving for y and writing y explicitly in terms of x and finding the slope. I'll go ahead and say the long way, and then I'll show you implicit differentiation, and hopefully you see, oh, implicit differentiation is way better. That's my hope. All right, so let's see if we can solve for y. So if we try to solve for y, we get y squared is equal to 25 minus x squared. And this is the part, where we take the square root of both sides, which gives us two different solutions for y. So either y is equal to the positive or the negative square root of 25 minus x squared. Now, if we're talking about the upper half of our circle, then we're talking about the positive square root of 25 minus x squared. If we're talking about the lower half of our circle, then we're talking about the equation y is equal to negative square root of 25 minus x squared. So we can find the derivative now. We can find dy dx, right, for this function here. But the derivative of this function will only be the slope for a line tangent to the upper half of the circle. If we find the derivative of this function, it'll be the slope of the line tangent to any point on the lower half of our circle. Now, we can actually calculate dy dx for both this function and for this one. Now I'm going to do what I did earlier, and I'm going to call this y sub 1 just to differentiate. Okay, so now what we can do is we can say, all right, dy sub 1 dx is equal to, let's see, it'll be 1 over 2 times the square root of 25 minus x squared. I am right now finding the derivative of this function here. I'm using the power rule. The square root can be rewritten as a power of 1/2. So 1/2 comes down. And then this radicand is now being raised to the power of negative 1/2. So that's what I've written here. But you're not done. Times, because this is the chain rule, times the derivative of your inner function, the derivative of this radicand, 25 minus x squared, will just be negative 2x. So negative 2x. We can rewrite this nicely by just writing negative x over the square root of 25 minus x squared. Now, again, this is the derivative for any point on the upper half of our circle. Now, if let's say we want the derivative now for a point on the lower half of our circle, which is exactly what we're looking for in this example. So dy sub 2, that all I mean by that is dy sub 2, I want to find the derivative of this function here with respect to x. So it'll be negative, and then 1 over 2 times the square root of 25 minus x squared times negative 2x. So we can simplify this by writing, let's see, just positive x over the square root of 25 minus x squared. Now, we'll use this derivative function to find the slope of our curve for any point on the lower half of the circle. All right, see, this is exactly what we want to avoid. We want to avoid having two derivative functions. All right, but it is what it is. In just a minute, I'm going to walk you through implicit differentiation. Hopefully, implicit differentiation will convince you that, it's necessary, it's efficient, All right, so let's continue. We want to find the slope of the circle at the point 3, -4, which of course is on the lower half of the circle. So we're going to use this second derivative here. So we're going to say dy sub 2 dx, right? Evaluated at x equal to 3 is equal to, we can go ahead and just plug 3 into this function here. So then we get 3 over the square root of 25 minus 3 squared. So then this is 3 over, 3 squared is 9, 25 minus 9 is 16, the square root of 16 is 4. So there we have it, folks. That is the answer. Okay, this is the answer. This is the slope of the curve at the point 3, -4. Now, that process that we just did was not implicit differentiation. I want to emphasize a few things again. I want to emphasize that we had to first, let me come all the way back to the beginning here. We had to first solve this equation for y. Again, which was not that hard, right? But we did have to solve for y. It led us to two different equations for y. Then we had to differentiate, and it gave us two different derivatives. Again, I'm trying to emphasize that that's not efficient. Two different derivatives, right? Which derivative you use or which derivative applies depends on what point you're considering, because they're asking us to consider the slope of the curve at the point 3, -4. We used this second derivative here, the second derivative function. We found that the slope of the curve is 3/4 at the point 3, -4. Now, let's do all of this work again, but this time around, use implicit differentiation. All right, so let me do this for us, all right? So like big line there, all right, to separate. All right, here we go. This is the equation they gave us. X squared plus y squared is equal to 25. So what we did earlier was we solved for y. Implicit differentiation says don't even bother solving for y. Go ahead and differentiate both sides of the equation, all right? So what we're going to do is we're going to take the derivative of the left-hand side and the derivative of the right-hand side. You notice I am not solving for y. Implicit differentiation says don't even worry about it. We don't have to solve for y. Now, you have to remember that y is a function of x. All right, so then this is going to be 2x, the derivative of x squared is 2x, plus 2y times the derivative of y with respect to x. Right here, folks, is important, okay? Remember, y is considered to be a function of x. So first use the power rule. 2 comes down, right? So it's 2y times derivative of y with respect to x is equal to the derivative of 25 is 0. All right. So what we can do now is just solve for dy dx. And when you do, you get, so isolate dy dx, and you get dy dx is equal to negative x over y. Stop right there. This derivative, first of all, notice that this is a single derivative, not two different derivatives, only one derivative. This one derivative will work or apply everywhere the circle has a slope. That is, at all of the points that are on your circle. So you don't need two different derivatives. You can use this one derivative for any point along the circle. Okay, so let's prove it. So first of all, notice this was not a lot of work here. I think the only tricky part is viewing y as a function of x. I mean, in essence, folks, you're viewing y as if it's y of x. That's really what you're doing. Y is a function of x. So if you prefer, you can rewrite this y right here, y squared, as y of x squared, if that helps. All right, so watch this. We already know what the answer is. It's 3/4. Remember, we did it earlier, right? So now they want the derivative, right, dy dx, to be evaluated, right, at x, or rather, at the point 3, -4. So it is -3 over -4. It's 3/4. That was the exact answer that you and I got earlier. Isn't that great? A couple things I want you to notice is that this derivative is pretty simple, right? That's good news. Not only is it simple, but it's written in terms of both x and y, as opposed to, I don't mean to make you dizzy, but when we go back up to what we did earlier, these derivatives, first of all, were more complicated. Where are they? Here they are. These derivatives were a little bit more complicated, and they were only in terms of x, right? A little more complicated, two different derivatives, and they're in terms of x. Whereas over here for implicit differentiation, we got a much simpler derivative, and it's in terms of both x and y. Okay? So you're going to see that happen, a lot, okay? You're going to see that the derivative involves both of the variables, x and y, okay? And it's a simple formula. So anyway, that's implicit differentiation, folks. So I showed you how to find the answer two different ways. I hope you are convinced that implicit differentiation is much more efficient. All right, folks, look at this brand new function. Y squared is equal to x squared plus sine of xy. See, if we did not use implicit differentiation here, you and I would have to solve for y. How would you do that? Solving for y here would be very, very, very difficult. So using implicit differentiation is much more efficient. All right, so let's do it now. What we're going to do is we're going to differentiate both sides. So we're going to do dx of y squared must be equal to dx of x squared plus dx of sine of xy. Now, again, do not forget that y is a function of x. So then the left-hand side is 2y times the derivative of y with respect to x is equal to 2x plus, all right, here we go. Now this is the chain rule. So the outer function is sine of x and the inner function is xy. All right, so first it's the derivative of the outer function. The derivative of sine is cosine, but it's evaluated at your inner function, times the derivative of your inner function, right? So let me actually open up a set of parentheses here. Now, the derivative of xy, so the derivative x times y, that's a product. So we're going to use the product rule. Wow, it's the product rule inside the chain rule. Okay, so the product rule of x for x times y, it'll be the derivative of x, which is 1, times y, plus x times the derivative of y with respect to x. So dy dx. All right. Our job now, folks, is to isolate dy dx. Isolate dy dx. All right, so let's do it. the first thing I want to do is I want to get rid of these, I want to get rid of these parentheses. So let's actually distribute cosine of xy. So then it'll be 2y dy dx is equal to 2x plus, I'm going to write it like this, y times cosine of xy. Make sure you do not, when you distribute right here, do not multiply the y and this y and make y squared. That would be wrong because this xy is part of your argument of the function of cosine. Okay, and then this will be plus, how do we want to write it? X dy dx cosine of xy. Okay, now we're trying to isolate dy dx, so I'm going to get all my dy dx terms on the left side. So I'm going to have 2y dy dx, and then minus x dy dx cosine of xy is equal to 2x plus y times cosine of xy. Next is I'll, let's see, maybe factor out dy dx from this left-hand side. So then dy dx times 2y minus x times cosine of xy, of course, is equal to the right-hand side. All right, very good. So then dy dx is equal to the right-hand side, which is 2x, plus y times cosine of xy, all of that divided by 2y minus x times cosine of xy. Please notice that this derivative is in terms of both x and y. And this one derivative applies everywhere that this curve has a slope. Okay, so that is implicit differentiation, folks. Great job. All right, cool. I think it's time for another example. Let's use implicit differentiation again. All right, we have the equation 2x cubed minus 3y squared is equal to 8. And they're asking us to find the second derivative. So they're asking us to find y double prime. Okay, implicit differentiation says don't bother solving for y. Implicit differentiation says that we'll only have one derivative function for any point along this curve. So let's go ahead and do it. So let's go ahead and differentiate both sides. Let's find the derivative of 2x cubed and then minus the derivative of 3y squared. Let's not forget that y is a function of x. And then, of course, the derivative of the right-hand side. All right, cool. The derivative of 2x cubed is 6x squared minus, here we go, the derivative of 3y squared, this 2 comes down, makes 6y, correct? 6y, but you're not done, times the derivative of y with respect to x, okay, is equal to 0. Our job right now is to isolate dy dx. So then dy dx will be equal to x squared over y. I'm going to go ahead and use this notation here. I'm going to say y prime, that's what dy dx is x squared over y. All right, cool. So we found the first order derivative, the first derivative. Now let's find the second derivative, okay? So let me just move this up a little bit. And let me change colors. All right, now y double prime. Y double prime will be the derivative of the first derivative, so the derivative of x squared y. Again, don't forget that y is a function of x. This is a quotient. This is a quotient, so we're going to have to use the quotient rule, all right? So let's do that. You know what? I think we're going to have to come back to this statement right here. I'm just going to put star next to it. I think we're going to need this statement later, I think. So just keep that handy, okay? Don't lose that. All right. So here we go. This is the quotient rule. So it is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. Okay, let's see if we can simplify this. So then this is 2xy minus x squared times y prime, but y prime is x squared y, so I'll make that substitution. X squared over y, x squared over y, over all over y squared. Okay, so then simplifying further, we get that y double prime is equal to 2xy minus x to the fourth over y, and then all of that over y squared. I think we can simplify this further. I think it'll be really nice if we wrote the first term 2xy over y squared minus the second term x to the fourth over y divided by y squared is equivalent to multiplying by 1 over y squared. So then this simplifies, y double prime simplifies as 2x over y minus x to the fourth over y cubed. This is y double prime. Isn't that great? And this was implicit differentiation.